Parallel.
Oh, yeah.
If it's parallel to the x-axis, it's dx. Parallel to the y-axis, it's dy for washers.
Yeah, because 0 plus 2.
I mean, for discs, yeah. Because I'm saying that because shells, the next method is going to be the reverse.
That's going to be gross.
And all you got to do, instead of trying to memorize everything in the world, see how it's built. Why does it make sense? So now watch. So I want to give you this handout before the end of the day. But real quick, how do I locate washers? How do I locate? I keep saying washer. How do I locate a disc? Here I would locate a disc on the y-axis, right?
Yeah.
For this y, there's a disc. For this y, there's a disc. Right? That's why, and if I rotate around anything that's up and down, any axis is up and down, I'm going to locate the disk the same way. Does that make sense? That's why, when I use a disk method, I'm going to do integral d whatever based on what I'm rotating around, right? So if I'm rotating around something parallel to the y-axis, it's going to be dy. Or on the x-axis, it's going to be dx. Which is a beautiful thing to tell you that my teacher never told us. And it just makes it make so much more sense right off the bat. You've got to trust me in that. You're like, all right, it's 0 right now, Jeff. I'm not sure how you could be less than 0 understanding. But I was actually at negative understanding.
Dx.
So let's see, how do you draw this? X squared. X equals 2. So x squared, I want to go from, and it's going to be with the x-axis too, right? The x-axis. So let's see, 0, 1, 4, right? And then here's x equal to 2. So the region that's created by the intersection of all those three, bam, bam, and bam, is this little region here.
So we're supposed to use
Wham,
this section? Or the...
What am I rotating around?
The x. But when
Is my region flush? What's a good word? You guys understand the word flush with the x-axis? Is my region up against the axis that I'm rotating around? Yes, it totally is. There's no room there, so it's not a washer. It's a disc. And again, washer method is freaking disc method. How do you tell the difference, though? Exactly what I just said. This one, why was it a washer? Because there was empty space between my region and what I was rotating it around. That's what tells me when to use the washer method.
So you're rotating around the outside of the...
I take this whole region and I treat the x-axis as the center.
Oh, okay, I see it.
That's what it means to rotate around something.
You're not rotating around the graph, you just rotate... Okay, I got it.
I'm taking that region and just spinning it around the x-axis. That's what I mean when I say rotate it around the x-axis. Kick ass. Alright. So what do I need to figure out? I need to figure out what r is. So we know we're going to do integral d what?
V or dx?
Yeah, dx, because we're going around the x-axis. It's parallel to the x-axis. It's amazing. So now I've got to figure out, so I want pi r squared dx is what I want. So if pi can come out, what is my r going to be?
X squared.
Yeah, in this case I'm starting at 0 and going up to x squared, so that my r is x squared. Alright, let me stop there. Is that, you guys, again, I mean, this is a new procedure. You got to figure out how to look at it, figure out how to get what you need. Now this is simple integral. From what to what? Sorry.
From 0 to 2.
Yeah, since I'm doing dx, it all depends on what x is doing, 0 to 2. So what's important here is it dx or dy? What is r? And then what are your boundaries on the interval? Right? What interval are you going across? So how do you integrate x to the fourth?
It becomes x to the 5th over by 1.
And you want to go from 0 to 2. 0 is going to make it 0, so just got to worry about 2. So I get
32 pi r squared.
32 pi over 5. I like it. How does that relate to... Well, this is not quite the same. Shoot. I wanted to relate it to that somehow. But if I use... Can you guys see? If I use square root of x, should it get bigger or smaller volume? If I use square root of x, well, it would be... shoot. I'm not quite doing what I want. If I use the function that was like this, Oh, you get bigger because I picked up this extra area and rotated along with it. All right. Let's try to do this one together because we haven't seen an off-axis of rotation, right? So it's not an axis of evil. I like the pity laugh. That's awesome. I'll laugh for you, Jeff. So we still have the exact same region we did before, right?
Yeah.
Exact same region that was over there. So let's see if I can do this again. Yay, Jeff. Don't celebrate too early. You learn nothing. But now I'm going to pick that. I'm going to rotate it around this.
Which is a dx.
So my radius used to start at the x-axis and go up, but now I'm not doing that. Now I'm going to start here and go out. So how far do I have to go? So two things. What method would this book call this? Because what's in the middle? The middle is empty space. So if I were to just use this as r, I would fill this in, but it's not supposed to be filled in. So I got to subtract that out. So what's the r outer? Oh yeah, let me do this in order. So we know, basically we already know it's going to be dx, right? Because it's, right, and we pull that? That's where you got to start, because that controls everything. So I do want functions of x, it's awesome. So r outer is x squared. Keep going.
Plus 2.
And to be official, now watch, just so you can get it when it gets all freaky, this really is the bigger one minus the smaller one. So it is x squared plus 2. What's the distance between these two? How do you find distance in math? You subtract. So it would be x squared minus negative 2.
Huh.
So if I had a shape and I was rotating around y equals positive 2,
It would be this shape.
then it would be minus, right?
2.
So again, in this case, it's totally going to be plus. I know some of you guys figured that out without the way I'm talking about, but trust me, you want to really realize why it's that when things get weird, right? Because I could put my axis of rotation anywhere. I could put it here. I could put it there if I wanted to rotate the other way, right? Okay, so no matter what's going on, you take the bigger minus the smaller. Yes?
How do you know that x squared is the outer?
Because where do I stop? Why did I stop my arrow there? What did I stop at? What's controlling this?
So you get a polynomial.
Where did that curve come from? Where did this come from? Isn't that the outer edge of the shape, right?
Yeah.
Okay, that's the outer edge of the shape. What controlled that shape? Why did I draw this? Where did this come from? What function? That one. That's the definition of that. So I start at negative 2, and I go up to y equals x squared. So how far did I go? X squared minus negative 1. X squared plus 2. Not only did I go x squared, but I also went this 2 in addition. Right? So that's how most of you guys got that, which is beautiful, but there's a more general way to look at it. What's r inner? That's easy.
4. R2?
2. From the axis. So really, in that case, you just want to control the empty space. What radius controls the empty space? Right? Yes, sir.
R inner will always be the empty space?
Yes. If the empty space is on the outside, then it's not really, you don't even have to control for that, right? Yeah, so our outer basically is to the end of the region, and our inner is the part you're going to cut out. So that must be the empty space in the middle that you're going to cut out. Maybe. So what was that again, sir?
2.
Yes, cool. Because that's how far away from the axis that is. That's how far it's empty. So then you go pi integral. What's x doing? Now here's where people freak out. But what is x doing? X is going from 0 to 2. So this is what I really, over time you'll start to get this. None of this other shit matters. This doesn't matter. If I draw the 3D in there, it doesn't matter. X goes from 0 to 2. That's the definition of that region. I don't care what other shit's going on. Do you understand?
Yeah.
Please understand that. Yes?
But how come in this example it was 0 to 2, but x went from 0 to 4?
Well, we were doing, on this one we were doing dy, right?
Oh, why is this one
So we were doing this one around the y-axis, so it was dy.
Up parallel to the x-axis.
So if it's parallel to the x-axis, you're going to do dx. If it's parallel to the y-axis, you're going to do dy.
So if it said x equals negative 2, then it would be parallel to the y-axis.
Exactly. And we got a problem like that coming up, right? I think I did. Yes, cool. Yay. So again, let me And the thing about this, if you understand why that is, how do I locate my disks? In this problem, how do I locate a disk? Right? So here, how did I locate a disk? On the y-axis. That y point is a disk. Right? That's where a disk sits. No. What's up? Do you guys understand? So, let me see. I'll tell you what. Let me give you this. This has got some nice visuals on it, and a lot of colors. Show us that.
If you make y, this is for y, x equals so x, where x equals -2, if it is -2, where y is equal to 0.
Alright, disk slash Kazan.
Okay.
Alright. So this picture here, watch. That's a much better representation of what I was trying to draw earlier, right?
Here
Okay.
we're rotating it around.
Alright. I just don't want to give this to you until you can understand almost half of this handout, more than half of this handout. Now you should be able to kind of understand. The shell method, you don't worry. You ready?
I can do that.
So yeah, that one is
So how do I, in this case, I'm rotating around the x-axis. So how do I find a disk? This disk sits at an x value, right? That's why the integral is dx, and that's why the integral is dx. Is that what we're at? and if I just turn that bad boy around, if I rotate around the y-axis, it's the same thing. So now real quick, I know we haven't talked about it yet, but just to show you what I mean. So when I do disks, if you just remember how you find a disk, that'll tell you why it makes sense that when it's around the x-axis, it's dx, when it's around the y-axis, it's dy. So that's how you find it. In the shell method, I'm going to locate my shell on an axis perpendicular to what I'm rotating around. That's coming up later. That's why it's going to be the other way around. So maybe you can look ahead to that and see why it makes sense. So there's a nice little washer. It's a beautiful, much better than I could ever hope to do, right? R inner, R outer. You guys kind of with me?
So when you have a washer, the way you set up your integral is always R
Outer.
minus R inner.
Yes. Cool. Because what's the washer look like? It goes out to certain, but then you cut the middle out. So that minus inner, you're cutting the inner part out. That's why it's always minus
R0, how do you figure that out? R outer.
You go from the axis all the way to the outer edge of the region. Right? So how did I figure out this R outer? I went from the axis all the way out to the outer edge of the region.
Okay, I see.
Okay.
Cool. I like it.
Yeah.
All right, where are we at here?
You get
Yes.
okay, so like x to the fourth plus
Yeah, so this would be x squared plus 2 squared, right? Everybody. Hey. All right. R outer is this. Are we all cool with that now? So you square it when you plug it in the integral, right? Because it's all based on areas of circles, these disks. Minus R inner squared, which is 2 squared, 4. So what do you do with this, of course? Oh yeah, sorry. What's the limits? Again, yeah, I know we did some weird shit here, but x doesn't give a crap. It's going from 0 to 2. Right? It's going from 0 to 2. That's what x is doing. 0 to 6. So then we get integral 0 to 2, x to the 4th plus 4x squared plus 4 minus 4 is gone. Yay. Is that cool?
Yeah.
Plus 4 minus 4 when you FOIL it out, so cancel that dude. So then you get pi times x to the 5th over 5 plus 4x cubed over 3. Don't forget how intervals work. That's all right. Start to mix and match the derivatives and integrals, and then bad things happen. If you mix integrals and differentiation, you're going to have a bad time. So now the 0 again. Always check this. If you have 0, it does kill everything, so I only care about 2. So then I get 32 pi over 5 plus 32 pi over 3. Neato. Now, real quick, this 32 pi over 5, does that look familiar to anything else on this paper? Maybe the only other problem we did?
Yes.
Yes. So you take this volume, that's a part of this, is interesting. So it would be weird to figure out what that is. Now, why is that there, you think?
Because if you subtract the negative,
No, but it's plus.
with negative minus.
So why would this volume be bigger?
Because there's
Because the empty space.
So if I how explains if yes,
rotation.
Basically, you're wrapping it around a longer.
beautiful. So if I wrap it around, if I'm really close to the axis of rotating around, it's not gonna go very far out. But if I further away, then there's a lot more to go around, right?
Right.
You guys kind of understand a little bit? All right, there's some physics in there too. Let's see. Let's do one more. Let's do one more. We'll leave that one for next time. So let's do this one together. Can you guys see where those meet? Can you guys see that? They obviously meet at 0, right? And where else do they meet? 2, because then they're both 4. Like. Or you can just set them equal to each other, subtract, factor, x times x minus 2, you get 0 and 2. Alright, so at x equal to 2, what's the output for both? 4, like we just said. Cool. So one of them is going to be a straight line to that, right? And that actually is that cone problem I did earlier, right? Remember that? That was the 2x was the cone, the edge of the cone. And the other one's going to be the parabola. It's going to attack it from the side instead of flank. It's going to attack. And it should go through one, and it did. I was very lucky there. Yay, Jack. Right. Doesn't really matter. So you get this nice banana that we're going to rotate. Yeah. And we're going around the x-axis again. So, again, you don't have to draw it in, thank God, for me especially. Yes. So I've got the cone problem we did earlier, but then I'm going to subtract this bit in the middle. So it's a lot like that problem we did earlier that was around the y-axis, if I remember correctly. So what's the r? So, and I'm going around the x-axis, so what's the
2x.
r outer going to be? Good. R outer is 2x. Because I start at the axis, and I go out until I hit the outer end. And then to get the r inner, I start at the x-axis, and I go out until I hit the first.
So 2x minus
First.
Yeah, x squared.
Yeah, so r inner is just going to be x squared. It's not minus or plus anything because I'm on the axis itself. I'm not off the axis.
Okay.
It's only going to be plus 2 or minus 3 or something if I'm off axis. But I'm on the x-axis, and that's 0. So that's why it doesn't show up. So then I get pi integral. And of course, the first thing I should have done is this, but we knew what this is going to be. It's dx. Right. Yeah, good. And x is doing 0 to 2. So r outer squared.
4x.
Good. 4x squared minus r inner. X to the 4. Cool. And then you just integrate that. Throw in your limits. Wow. Coolness. So just so you realize this, I don't know if you guys realize this, but if you notice on the homework sheet, next week, of course, next week is Thanksgiving, right?
Yes.
I'm giving all of us Wednesday off. I don't know if you noticed that.
You did?
Next week?
Yay. So, which just means we need to get through this.
Yeah, okay. Wait, is our test
So-
the week after we come back?
The test is officially on Thursday, but remember Thursday, you guys, have you noticed that?
Sure.
On the homework sheet, it says Thursday. I'm going to ask if you can move that to Wednesday and give you some more time.
Oh, like do it all on Wednesday?
Do the test on Wednesday, yes. And then we can treat Thursday as an extra review day.
Wait.
Listen up. We'll talk about it tomorrow. Just look at the homework sheet and you'll see what I'm talking about.
Do we have one more test and then the final?
One more test and then the final. Yeah.
The final is Cuban.
Finals, come on. Come on.